Hi guys, it's a guy Olumide, and today we are gonna be solving another one of the most commonly asked tech interview problem by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. So the topic or the problem for today is the first and last occurrence of a number. Is a commonly asked DSA question in tech interviews. The problem statement states that given an array of integers sorted in non-decreasing order, so non-decreasing order means increasing or ascending order, so return the first and last indices of the target number. If the target is not found, return the sets -1 and -1. I mean the list -1 and -1. So the problem actually wants us to look for a target in an array. We'll be given an array of sorted integers. So, and we will be given a target value now, just like in this example. We are giving array nums and we are giving the target value 4. So, fine. Want to look for the first occurrence of the target value 4 inside the array nums, which is here, and also want to look at for the last occurrence. So these two indices, like now, if you look at this, the index 1 and this is index 0, index 1, index 2, index 3. So this the first occurrence of the target 4 in the array nums actually occur in the third index, and that's why we have it here, third index. So and that is why you have it here. So and then the last occurrence occurs in the fifth index, and that's why we have this pair return 3,5. But in case if we not find the target inside the array, we should just return the pair -1 -1 to signify that we could not find the index and the particular target in the array. So this is the explanation. The first and the last occurrence of the number 4 are actually indices 3 and 5, just like we explained. A brute force approach to solving this problem is to perform a linear search across the array to search for the first and the last occurrence of the target. So just a linear search. Anytime we first get into the first time we encounter a 4, we record it, we store it, and the last time we add another 4, we store it again. We store the position and then we can return it. So but one thing is that linear time takes on. It means that it's gonna take on time iterate through each element in the array depending on the length of the array. So but we can use the fact that the array is sorted. We can use it to our advantage and solve this problem using binary search algorithm, which take O of log n, which is far more efficient than the linear time algorithm. So we're gonna be taking advantage of the fact that this array is sorted, and we'll be using the binary search algorithm to solve this problem. Now the challenge with using binary search for this problem is that we need to perform we need to search two separate occurrence of 4. Don't forget the problem asks us to return the first and the last indices of the target number. Fine, we know about binary search can help us to search for 4 in the array. You understand? It can help us to search for the lower bound and the upper bound, meaning that the first and the last. But that will require two separate binary search function or method. So the first one to go for the first indices to search for the first occurrence of the target, while the second binary search to search for the last occurrence of the target. So this is the same as creating two binary search. One to search for the lower bound. Lower bound means that the one to the left, that is the first occurrence that is to the left, and while the upper bound means that the second occurrence, that is the one that is further to the right. So those two binary search is what we're gonna be doing. Now let's talk about the first one of the binary search that we'll be doing, which is the lower bound. I hope you understand what I mean by lower and upper bound. So because the question asks us to find the two indices of the target, or the two occurrence, the first occurrence of the target in the array and then the second occurrence, so we'll be needing two binary search methods to do this. Mean that a binary search is just gonna get us either one of the first occurrence or the last occurrence. So to get both, we need two binary search, and then we can call this the lower bound and the upper bound, just like we can see right here in this visual. We see that this is the lower bound. Fine, 4 4 4, the 3 4 here actually are the target and they are correct, but we are interested in finding the position of the first occurrence and the very last occurrence, which is the lower bound and the upper bound. So now in searching for the lower bound algorithm, we are going to consider 3 conditions based on the value at the midpoint. We're going to considering 3 conditions. The first condition is whether the value at the midpoint is greater than the target. Don't forget that when dealing with binary search algorithm, we used to have the search space. If you go watch my previous video, we used to have the search space, which is one at the left, one at the right. So it's just like a window, a boundary that actually that define the values that we are considering, every possible value that could be the target. So just like in this array now, for instance, the search space will be right from the index 0 to index this particular index n-1. That's cover the entire array. So now, and then we discuss how we are gonna get the midpoint, or let me say the mid value, just by using left plus right divided by 2. So we can jump at the middle, because that's the advantage of using the binary search. It does not actually it does not flinch through the array one by one. It actually jumps to the middle, and depending on some condition, and these are the condition, is going to determine, okay, where are we going, toward the left or toward the right. So if when it is greater than the target, when the mid value is the midpoint, understand, is greater than the target, is one condition that we'll be considering. When it is less than the target, is one condition we'll be considering, and when it is equals to the target. So we are going to be understanding it further right in this particular page. So now let's consider when the midpoint value is greater than the target. Fine, we have placed our left and right pointer at our search space. So we define our search space to be the 2 extreme of the array, so that it can cover every value in the array. And then we define our mid value to be at this center by saying that left position 0 plus 12 divided by 2 will give us 6, and that's the mid position. So now, depending on the value of this mid position, so we see that the element at this position, mid position, is 5. Now 5 is greater than the target because our target is 4. Look, our target is 4 right here. So 5 is greater than the target, and because of that, what we do is that we narrow our search space to the left by setting right equals to mid minus 1. And why we are doing this is because this array is sorted fine, meaning that if the midpoint here can be greater than the target, everything that follows it will be greater than the target, and we are genuinely looking for the target exactly. Hope you understand. So the mid value is greater than target, so is everything that follows it, and because of that, we are going to narrow it to the left by shifting our right pointer to mid minus 1, so that our right pointer will lay just behind the mid value, which we can see here now. So why we are not putting it anywhere else, or why we're not putting our right pointer at the mid itself, is because the value at the mid is greater than 4, is not equals to 4, and we are genuinely looking for exclusively looking for a value that is equal to 4. And because the value at the mid is greater than 4, definitely every value that follows the mid will be greater than 4. So we have to narrow our search space to mid minus 1, just like here. Now let's consider the second condition that we can encounter during our binary search. So the second condition is when the midpoint is actually less than the target. Now we are trying to continue this same problem, you understand. Don't forget, we have we have narrowed our space and search space by shifting right toward the left, and to mid minus 1. So now if we pick the center again, where will the center be? The center is gonna be the middle is gonna be at this index 2 with this element 3. Hope you understand. So fine, the element at this particular middle here now is 3. 3 is less than the target because the target is 4. What do? We are gonna narrow the search space to the right. So in the process of narrowing the our search space to the right, we're gonna be shifting the left pointer from the initial position, which is 0. We're gonna be shifting it to the position 3 now, which is just one position past the middle, because now at this point the middle is 3. The middle value is 3, and 3 is actually less than the target we are looking for. So 3 and every other thing that comes before 3 actually need to be excluded. So we have to shift our left pointer to mid plus 1, and that's why it's currently at mid plus 1. So that is for in a situation whereby the mid value is less than the target. So now the last situation, a value is, when we compare to value, is always going to be less than or greater than or equals to. Those are the two. Any number you're trying to compare, if it is not less than, the second number is going to be greater than the second number. If it's not greater, it's going to be equal. So that's why we have this third condition. In case in a case whereby the midpoint value is equal to the target, you understand, what we're going to do is that, okay, now we have a very nice scenario which is still the continuation of this example. Don't forget that this example, we first use it for a situation whereby the midpoint is greater than the target, and that's how we are able to navigate our right pointer to mid minus 1, and that's why it landed at this position 5, with the element 4. So, and then we use it similarly for a situation whereby the midpoint is less than the target, so whereby the midpoint fall right here. So, and then we shifted our left pointer to mid plus 1, so which is at position 3. So this same scenario now is what we are going to be using, because right here, considering the left pointer to be at position 3 and the right pointer to be at position 5, the midpoint will be 3 plus 5, right, divided by 2, that is 4. So the midpoint is currently at the middle right here, and the midpoint is actually equals to 4. So what do we do? Because this binary search is the lower bound binary search, don't forget we have to return the first occurrence and the last occurrence, right? Because this one that we're explaining, right, just like I have it here, is the lower bound binary search. We are going to be setting our right to middle here. So why we are setting our right to middle is because we want to check if there is any more value that is equal to the target to the left. So we have to navigate our space, our search space to the left by shifting the right pointer to mid. But if you notice, we've been shifting the right pointer to mid minus 1 before, but why we need to shift it to mid, exactly mid here, is because mid also satisfy the condition, right? So this might the value at mid might be the first occurrence. There might not be any more value, it might be the lower bound, you understand? So we don't want to ignore the middle position and the middle value from the space tree. We want to include it. Don't forget, if we set our right pointer to mid minus 1, we have exclusively remove it from the space tree. So we don't want to remove it, we still want to have it there. So we are going to set our right pointer to mid. So setting the right pointer to mid, now we are going to find our middle points or midpoint value again. So, and at this case it's going to land at the left pointer. Don't forget, look, the left pointer is pointing at the position 4 right here, right pointer is pointing at the next position 4. So if we find the middle, it's just like 3 plus 4 divided by 2 gives us 3 back. When we truncate, 3 plus 4 gives us 7 divided by 2 gives us 3.5, but that's still 3 because we're going to truncate. There's no index of 3.5, so we only have index of 3 and 4, so we're going to go for 3, and the middle pointer is going to land at the same pointer that the left pointer is pointing to. So now again, we're going to look at the condition. Don't forget that based on the midpoint value is what is going to determine where we are going to navigate to. So now the midpoint value is pointing at 4 again, you understand, and therefore look at it up here, we are going to set our right to mid again. Why? Because we want to keep adjusting the right pointer to so that we can get to the very first occurrence of that value. So we are going to shift our right pointer, and now we shifted our right pointer and it fall on the same position as the mid position, which is the same position as the left pointer. Don't forget, look at it here, that they are pointing at the same position. So right now is also pointing at that position, and because the left pointer is now equal to the right pointer, so we are gonna loop out definitely because they are both pointing at the same value, and now the value they are both pointing at is 4. Definitely we are just gonna return this position 3. So this position 3 here corresponds to the first occurrence of that target target 4 in the array. Now let us consider the other aspect of the binary search. Don't forget we'll be performing 2 binary search, one to find the first occurrence, which is the lower bound, the other to find the last occurrence, which is the upper bound. So for the upper bound binary search now, the same condition apply based on the value at the midpoint. So when the value at the midpoint is greater than the target is the condition, or when the value at the midpoint is less than the target is another condition, just like we discussed for the lower bound. So and when the value is equal to the target is the third and final condition that we can have. So and then the what we do, and how we attend to these 2 conditions are the same. That's why I mark them. So meaning that they are the same as the lower bound that we defined. Why? Because we are still dealing with the same target. So when the midpoint is greater than the target for both lower bound and upper bound, what we do is that we want to navigate to the left. We want to shift our right pointer to mid -1 so that we can navigate away from that midpoint, cause that midpoint upward in the array will always be greater than the target. So similarly, when the midpoint is less than the target, we want to narrow our search space to the right by shifting the left pointer to mid +1 so that you can effectively remove every value from the midpoint downward. I mean to index 0. We effectively remove it from the search space. So but now you see that they are the same. Now the same logic applies, but the difference now will occur when they are equal. So when the midpoint is equal to the target, we don't want to navigate toward the left to find the first occurrence of the target. Rather, want to navigate toward the right to find the last occurrence for the upper bound, and that's where the difference is. So now let's consider a situation whereby the midpoint value is equal to the target for the upper bound now. So this is a good scenario whereby the midpoint become equal to the target. So don't forget that this same example we have considered it. So it's right here. We have considered it now, but now we want to be applying the logic for upper bound, not the logic for lower bound. So and what will happen is that whenever the midpoint equals to the target, that is nums of mid is equals to target, just like here we see that the element here is equals to target 4. So and what we're going to do is that we're going to set our left to be equals to mid. Why? Because we actually want to navigate toward the right. We want to keep looking for the last occurrence of that target so that we can get to the very last, and we can do that by navigating to the right by setting the left pointer on the mid position. We don't want to set it past the mid position. Why? Because we don't want to lose that value. So we need to set it exactly on that middle position so that we can include that occurrence, this particular for, inside the search space. So and that's what we did here. We shift it is at position 3 now. Now we shift it exactly to the middle position, just like we have written here, and now it's at position 4, which is the middle position. So again, what we do is that we are gonna find the midpoint, right? We always, binary search is so simple. It's just about doing the same thing over and over again. So again, we want to search the midpoint, and how do we search the midpoint? By using the left plus right divided by 2. So it's gonna fall on the left, because now left is there are just 2 numbers remaining in the search space, the position 4 and the position 5. So if we find the median, it's gonna fall at the position 4, which is the left position, just like we can see it here. And because of that, if we evaluate based on this middle position now, it is equal to the target. It satisfies the condition of being equal to the target. And what we do again is that we set our left pointer to the middle position. But you will notice something, that the left pointer and the middle position are both pointing at the same thing. So setting left pointer to the middle position is just like leaving it just as it is, because they are already referencing the same position. And if we do this again, just like I tell you about binary search, is just about finding the median, trying to do some comparison, that is the median greater than or less than the target, or is it equal to the target, and based on it narrowing the space tree. So right now the middle position is still at we are gonna, when we find the middle position again, because the left remain the same and the right remain the same right from this place, as a result of the left and the middle position pointing at the same thing, when we set our left pointer to the middle position, it's just gonna remain. Why? Because left is equals to middle right from time. So and when we try to do it again, when we evaluate the middle position, it's gonna fall at the left pointer, right? Falling at the left pointer, I just want to see what I said the other time again, because that's what is happening again. So when the middle position fall at the left pointer, what happened is that, okay, the middle position fall at the left pointer is fall at this particular element 4, and because 4 is equals to the target, norms of mid is equals to the target that we are looking for, right? So what we're gonna do is that we're gonna set the left to mid. You understand? Norms of mid is equals to the target we are looking for. So what we're gonna do is that we are gonna set left to mid, so that we can find a more occurrence of 4 to the right. So we are trying to narrow the search space to the right. So by setting left to mid, make sure we are making sure we are including mid, so that because mid also satisfy the value at that mid position, satisfy the condition. So, and setting left to mid is just like leaving left where it is. You understand why? Because mid is already at left, so setting left to mid will just result in the same thing, and then that's how it goes on and on and on. Mid is not leaving left is not leaving mid, and then it results in an infinite loop. So how are we going to break through out of this infinite loop that occur for the upper bound binary search, whereby whenever we found the target, we want to look for the last occurrence by shifting the left to mid. Okay, let's see what's really happening there. So we see that when the left and the right pointer are just one step away, when it's remaining 2 value in the search space, we've navigated and narrow, and now it's remaining just 2, left and right, laying side by side. When we keep using this mid position, evaluating this mid position as left plus right divided by 2, mid position is always going to end up at the same position as left. You understand? So, and because of that, we have to bias the mid position to the right. So as a general rule, to solve the problem of debugging or of infinite loop in the upper bound binary search, generally what we used to do is that we used to bias the mid to the right. And what it means is that instead of just evaluating mid to be equals to left plus right divided by 2, we will bias it to the right by setting a +1 to it. After doing left plus right divided by 2, we're gonna set a +1, so a +1, so to hit, just like I'm doing right here. So that way it's gonna be biased to the right. So, and instead of the mid pointing at the left now, right, it is at the left. You understand why? Because left plus right divided by 2 will fall at the left, but the +1 that we add now, it's gonna bias it to the right. So, and it's gonna be pointing at the right this way. You understand? You can look at it in the situation of 3 plus okay, let's consider this situation now, right? Let's consider this loop. 4 plus 5 now give us 9. 9 divided by 2 will give us 4.5. So by truncating, because we are dealing with indexing, so we are gonna truncate and we are gonna return 4. So although it's 4.5, but we are gonna take it as 4 so that we can index, and that's gonna lead us to the left pointer. But because we are now biasing to the right, we are gonna be adding 1 to that 4, so that's gonna lead us to 5. So that is exactly what we did here, and that's why we know when we bias it's gonna go to the 5. So now it means that to solve the problem of infinite loop for upper bound binary search, we are gonna be using a biased midpoint, so which is biased to the right. So whereas we don't need to do that for the lower bound, because fine, lower bound worked very well, we explained this up here, and it worked very well without giving us infinite loop. But for upper bound, we will be using the value, our mid value will be equals to left plus right divided by 2, then +1. So now let's look at the application of that same thing. At this point now, this is the previous point that start to give us multiple loop, infinite loop. So we are gonna return back there and use this new bias midpoint. So right now we are gonna set our left to mid, just like we explained. And what I mean by that is that, okay, the mid position is at position 4, right? The mid pointer is at position 4, and then the value at that position 4 is 4. So because 4 is equals to the target that we're looking for, we want to set our left to mid. I hope you understand up to that point. So when we set our left to mid, so our left is gonna come from this point, from this previous 4 that is here now, is gonna move to this new 4 that is here, right? Now when we now evaluate the midpoint again, instead of the midpoint narrowing to left pointer or coming to this left pointer, because we are biasing it now, it's gonna be adding a +1 and it's gonna be coming right here, and because of that we are gonna be able to exit the loop. Why? Because okay, now that it's falling here now, right, it's not falling at left, it's not falling at this right, because we biased it. Now when we look at the value at that position, we say that the value that the midpoint is actually pointing at is 4, and because 4 is equals to the target we are looking for, again we are gonna shift our left pointer to the right, so our left pointer to the mid position, sorry, and because of that, so left pointer is gonna come right from here, it will come and meet the mid position here, just like we have it in this diagram. So it's moving from this previous 4 here to this new 4, and automatically the left and the right pointer are now pointing at the same position, position 5. So and definitely we can return at that point because they are now pointing at the same position. So this way now we have effectively solved and resolved the infinite loop for the upper bound by using a midpoint that is biased to the right. So that is just all we need to know concerning this to solve this problem. So we're gonna be going to the code implementation now. Alright, let's move into the code implementation now for the first and last occurrence problem. So to solve this, we're going to be defining a function first and last occurrence that's going to be collecting the norms, which is the list of integers that we want to search the targets in, and we're going to be collecting the target as well, so which is an integer, and eventually we'll be returning a list of integers. Don't forget the pair of the first occurrence and last occurrence of the target that we are finding in the array. So it's a list of integers. So fine, let's pass first and let's define our let's define the parameters we're going to be using, which is the norms and the target. So right here is our parameter, the norms and the targets. So we can even write the print. Let's put down the print, so it can just, so we know that we are passing in the norms and the targets so into it. So right now let's continue with the code implementation. So what we want to do is that we'll be defining a function. Don't forget we talk about using two binary search method, one to get the first occurrence and the second to get the last occurrence. So let's call this the first to be the first occurrence, and this one is gonna get us the lower first occurrence corresponds to the lower bound binary search. So I'm gonna be creating a function lower bound binary search that will represent the first binary search for the first occurrence. So it's gonna be collecting the list and the target. So and then we're gonna be defining the second. So this one also will be the lower bound binary search that's also gonna collect the norms and the target. So but now it won't be lower, it will be the upper. So right now it might look somehow, but what I'm trying to do in essence is that we need to perform two binary search. Each binary search is gonna go get us the position of a target, but now we are being specific. The first is going to get us the first occurrence, the first position, while the second binary search, which is the upper bound binary search, is gonna get us the second or the last occurrence actually of the target. So and we'll be collecting it using the variable first and second. So what I want to do is I want to return first comma second. So and now let's now carry on with by defining these two functions. So let's define the first one, the lower bound binary search, that is gonna help us get the first occurrence, which is the lower bound. So norms and targets. So right here now we'll be dividing our left and our right. Fine. So it's just a normal binary search, you understand? So just that this one is focused on getting the lower bound, which means the first occurrence of that target. So we are still dividing the space and the search space to be 0, len of norms minus 1. So don't forget that the search space range between the first element in the array to the last element in the array. So we are considering every element in the array. So now while left is less than right, why? Because the moment left become equals to right, we want to return because they have gotten to a particular value. So they have gotten to the last value that navigates the search space and reduce it to one value. So we need to return and quit the loop at that point. So now the difference now is that in creating the mid value for the lower boundary, we will be using our familiar left plus right modulus 2, so that it to truncate it, divided by 2 to truncate. And then if norms of mid is less than the target, what do? We have to narrow our we want to narrow our array to the right. Why? Because the mid pointer, you understand, is pointing at a value that is less than the target. So every value before that value, even up to that mid pointer, should be ignored, should be removed from the search space. And we can do that by setting our left to mid plus 1, so that it will divert away from that position that left and that mid is. So but in a situation whereby norms of mid is actually greater than the target that we are looking for, so we want to narrow it to the left. So by setting right to be equals to mid minus 1. And what I mean by this is that because norms of mid is greater than target, definitely every value from that particular pointer, that mid pointer upward, will be greater than the target. So we want to narrow our pointer, our search space, by shifting the right pointer, which is at the extreme, to mid minus 1. We are even going to remove it away from the mid itself by shifting it one step away from mid. That's what mid minus 1 means, because mid itself is not equals to target, it is greater than target. So it is out of the possible value that are equals to the target. So but in the last situation whereby norms of mid is equals to target, we've considered when it is less than target, we've considered when it is greater than target. Now in situation whereby it is equals to target, we want to set our right to mid, right, because why? We are setting our right to mid because fine, we've gotten to a midpoint that is equal to the target, but we want to find the first occurrence. So we keep on navigating it, the right pointer, narrowing the search space toward the left, yes. So but putting in mind that mid itself is part of the possible value, so we're not gonna say right equals to mid minus 1. We're gonna put right exactly at that mid position, representing a value that is equals to the target that we're looking for. Now this is the loop that we have, and then once we exit this loop, we're going to return. So we're gonna return norms of right. So that is if norms. So we won't run out of it's just trying to catch exception. So we won't run out of index into an index error. So if norms are norms of right, so we're gonna return norms of right, else we're gonna return if norms of right equals to target, so else we're gonna return minus 1. So what we are doing right here is that fine, once we exit the loop, we are gonna exit the loop whenever left and right become equal to each other, and at that point we are at the final, the search space is now remaining just one element, just one value, and then we are left with that value. So we're gonna check if the value is equals to target. If it's equals to target, then we're going to return that value. Otherwise, we're gonna return -1. So we should be expecting in this call to lower bound binary search now, we should be expecting either a value or -1 in case if if the index does not exist in the array. So if the target does not exist in the array. So now let's define the second function, the upper bound. So it's also going to take in the norms and the targets. So, and similarly, similar things apply. We're going to be dividing our left and our right search space to be 0, length of norms -1, and then while left is less than right, same thing apply. So we've discussed in the logic that what just differs is how we define the midpoint for this one. So we'll be defining the midpoint as left plus right modulus 2 plus 1. So we are going to make it biased to the right, so that we avoid the infinite loop. So while if norms of mid is less than the target, we are going to, if norms of mid is less than the target, we are going to be shifting the left pointer to mid plus 1, just like we explained for the same case applied for the lower bound binary search. So we want to narrow it by shifting the left to the right to mid plus 1. So but in the situation whereby the mid pointer, the value at the mid pointer is greater than the target, so what we want to do is that we want to shift our right pointer to mid -1. So because the value at that midpoint is greater than the target, so we need to narrow the search space to the left. So but in a situation whereby the value is equals to the target now, so which is else, if it's not less than the target, if it's not greater than the target, then it's gonna be equals to the target. So, and in that case now we want to narrow it by setting left to mid. So don't forget that for the first one set right to mid, now we're gonna be setting left to mid because we really want to find the last occurrence, so we should keep narrowing the search space to the right. So, and after the while loop returns, we're gonna return the same thing just like we applied there. So it will be norms now of norms of left. So if norms and norms of left is equal to, so if it's the target, if the value is the target, we are gonna return norms of left, otherwise return -1 if it's not the target. So now we have defined both functions for the lower bound binary search and the upper bound binary search, and we can run the code now. Right, I run the code now and we add some errors because previously it returned -1,5. So, and where I noticed that the error is that the problem statement at us is not asking us to return the value. We already have the target value, so norms of right is already equals to target, fine. So we don't need to return norms of right, we actually need to return right itself. So we are asked to return the position. So the position is what we are asked to, the index is what we are asked to return, not the value at that index. So, and then secondly, this is the lower bound binary search now, so we are dealing with the left position, not the right position. So it's supposed to be norms of left, not norms of right. Why? Because don't forget that we are making the right, we are actually narrowing the search space to the left by setting right pointer to the middle pointer, because we really want to get the first occurrence. I mean for the lower bound binary search, we want to get the first occurrence. So we are going to be returning the left position if the value at that left position is equal to target, not right position. So it's supposed to be like this. And similarly for the upper bound binary search too, so we are supposed to return the right position. Why? Because we are narrowing to the right position. If norms and norms of right, we are dealing with the right position and we are narrowing to the right. So, and bear in mind, we are not returning norms of right, we are not returning the value at that position. Rather, we are interested in the index position, their respective index position, not the value at those positions, because we are already given the target value. So we just want to know the position of the first occurrence and the last occurrence. So let's run the code again. And right here we have it printed as 3,5. So which is correct, because the first position is at position 0, 1, 2, 3, and the second position is as 5. You know, when the first position is at 3, the second position is at 4 and 5. So we got it correctly. So that's how we solve the problem for the first and last occurrence of a target of a number in an array. Thank you.